another data structure. Name it stack. So stack the data structure that use algorithm or the concept of the last in first out. That's mean last element that enter the stack will be first element going outside the stack. So what does that mean? So I will show you how. If I try to draw the stack, I will use this pen and it would support the stack in this way. So think about it as a stack. So a stack would say it this way. And here you go. This is my stack. I just define how many elements be in this side stack. It is supposed in this way. This is my stack. This is basically my stack size. Let me suppose my stack size is 1, 2, 3, 4, 5, 6. That means stack size I have it here is 6. Okay? So basically, you say, okay, we define the stack and you say the size is 6. Now if I ask you, hey, add element, for example, add 5. How you would add 5? You say, okay, take the 5 and add it here. How much the top? First I have it, top is 0. When you add it, the top B, you increase the top by 1, so the top be 1, and you add 5 here. That's cool. Now I want to add another element. I want to add 8. So you'd say, okay, increase the top by 1, so the top be 2, and add the element in the index of 2, is 8. Now I want to add more elements, so we suppose add 4. You say, okay, increase the top be 3, increase it by 1, and take 4 and add it in the index of 3. That's mean 4. And you continue same concept, like add 11. You say increase the top by 1, so the top be 4, and you add 11. So I say add 1. You say increase the top by 1, so the top be 5, and you say adding 1. Then add 6. You say increase the top by 1 and add the element 6. Now I say, okay, add 7. You say, wait, the stack is full. I cannot add more. You say, hey, I cannot add it. So hey, ignore this step. This cannot be added. Now if you want to take element from the stack, how you would take it? When you want to take element from stack, you take the last one from the end. So how the procedure for taking the element? First of all, you do the top or the pointer for top, you take it down. So you say, okay, now just let me remove this so you would understand how the top is working now in the reverse way. So the top is 6. First of all, you say, okay, the top, oh, the pen is not good. So I say, okay, so another pen. You say, okay, top equal 5. Now you could delete the element. You say, okay, remove this element. Okay, now you want to delete 1. You say top equal 4. You say, okay, now you could delete the element. So first you reduce you take down the top 1, then you remove the element. You want to delete 11. You say top equal 3. Then hey, you could delete it. If you see when you add, when you delete it, you delete in sequence. The last one coming inside the last one you added to be the first one is going out. Now you want to delete the last one. You say, okay, top equal 2, and yay, remove the 1. Remove the 4. You want to delete more. You say top equal 1. Hey, remove this one. You want to delete 5. You say, okay, top equal 0. Delete 5. You want to delete more. You could get error. Why error? Because the stack is empty. You cannot delete more. No more data in the stack. So this is a basic representation of the stack. So what's the basic example you could get from this one? If I give you this number 1, 2, 3, 4, and I want you to reverse them. How would you reverse them? You say, okay, I would add them in the stack. Add 1, 2, 3, 4. Then just pop them from the stack. So when you pop, you have to first pop the 4, then pop the 3, then pop the 2, then pop the 1. So if you see, when you insert it, we insert in 1, 2, 3, 4. When you take the up, we take in 4, 3, 2, 1. So this is the basic representation of the stack. This stack now you think about how you would represent this stack bytecode. There's 3 ways to represent the stack bytecode. You could represent it using array, normal array, as we show you, array with size 6. You would represent it using dynamic array, like with the size is doubled, and that's what you see in Java. They use direct implement using dynamic array, or you could use linked list, and this is the better one for represent stack for the size. Not better one in all cases, as I told you, in most cases. So you could use all of these, and we will discuss them in the code how we would represent all these 3 data structure. Now let us talk about the big O notation and how we find them. So let us start with searching or access. If you want to search for element, like for example 2, how you would search it? You would take n time until pop 1, pop 2, pop 4, pop 3, pop 2 until you find it. So this one you take n time. So searching take n time to search element. Access to element, same thing. It would take O of n until to access any element, because you have to go in same direction when you enter or when you move element. Now let's talk about 2 next concept. When you want to insert, how you insert element? You would insert it in the end. So to take one process one time. So take O of 1. Because you just insert at the end. You cannot insert in the middle of the stack. This is the concept of the stack. You cannot insert, you cannot add, now I ask you add 5, you say add 5 in here. You cannot. When you add it in the end. This is the structure of this data structure. So take off 1. Delete, same thing. When you delete, you could delete only the last element. So when you delete this one, then this one. So take O of 1. So yes, this is sorry, this is the big O notation for a stack. So see them, see search, see access, see insert, see delete, see how the stack is working. So now next, when you see